Se você achar que está unidos, depois Fernando, você está ouvindo? Então pode apresentar ele.
Okay, super. Okay, so Carl, thank you very much for accepting the invitation to talk here at our meeting, celebrating 100 years of the famous papers of Schrödinger and Heisenberg. And well, Carl is someone that I've been working closely the last 10 years, at least. Okay. We did a lot of work on computation of quantum distribution functions in the Latin QCD. And this has been most of the Carl career since the beginning of his PhD, since he started the Latin physics model operations. And he has for a lot of work in Latin QCD. He has been in Wilson Prize, 2011. If I recall. And currently he's the director of the Center for Quantum Technology and Applications in Quântica, which is a very close to Berlin, and it is affiliated to DESI. Carl is currently one of the big names in quantum computing here in Germany, and he's going to talk to us today about the future perspective for scientific computing using quantum computing. Carl.
Thanks a lot for the invitation. It's really a pleasure to give the presentation here. And what I want to do in this presentation is really to give you an idea why I say that quantum computer could be a perspective for scientific computing. And my outline is that I will give you a short intro to quantum computing. We had already a presentation before that really told you about it. And then my applications today I selected to be quantum dynamics in 1 + 1, 2 + 1, and even 3 + 1 dimensions to really show you where we stand with quantum computing and that we are really, or that we are about to leave the era of baby steps and really go into 3 + 1 dimensions. I will touch upon the modern and gate theories, and then phenomena like real-time dynamics and what Fernanda mentioned, quantum distribution functions. The sound from your side was really bad, so if you have a question during my talk, please type something in the chat. Fernanda will watch this and interrupt me if there is any question, so please don't hesitate to interrupt me and write a question if you have it. I want to tell you where I'm coming from. I'm the head of the Center for Quantum Technology and Applications at DESI, at this Zeugen place close to Berlin. We are doing networking, we are doing scientific exchange, training and outreach. We are working together with governmental agencies, with industry, and with academia. And in this house that I envisage here, we are giving support to this governmental agency and industry academia, and we can also give them access to quantum hardware. We have a license agreement with IBM, which gives us the complete access of all of the IBM quantum computers, and through us, through our house, people from these pillars here can get access freely to quantum computers. And this is very nice. We can ask for income. We might need to pay for this. And the point is, since this is a house, I really want to have a house, so I want to also have some flowers at the cat, and you can imagine which cat this is. This is the present group. It's more than 20 people who are working on quantum computing. And I'm proud of this group because there are 50% male and 50% female members in the team while working this. And this is really very rewarding. What we are doing in the center is quantum simulations of quantitative medical models, both from matter and energy physics, and these are really models that are sign-affected and also real-time phenomena to really see what can we do on the quantum computer for phenomena like scattering in real time. But we are also doing optimization and classification. You saw in one slide before, there was the traffic control, and we are looking at flight gate assignment, meaning that we try to find with the quantum computer what is the optimal path through the airport to really post the flights and the gates at the right time at the right place, such that you as a passenger get an optimal connection. So this is really classical optimization. And the same setup we can use for particle reconstruction and jet classification, for example, at a Large Hadron Collider. We are also active in medical applications to do gene and X-ray classification in order to detect cancer in a very early stage. We have a little paper about this. Other activities are factoring to post-quantum cryptography, final diagrams, and matrix models, and many more, also fluid dynamics. We provide a lot of training in quantum computing, we are making people quantum ready, and we do a lot of algorithm development, expressivity of quantum circuits, controllability, and web starts. And as a side project, we are also doing quantum art. We are doing quantum computer music, and we are doing quantum painting. And from the 9th to the 11th of July in Seoul, at my center, we had a workshop where we brought together more than 40 people who were discussing about what one can do with quantum computer music and quantum painting. It's a side project on its by itself, also very interesting. I want to mention that I also have a Dara chair. The Dara chair is a European tool to be new developments in vital countries. And that was 2.5 million euros to build the quantum computing in Cyprus, where we again want to develop applications of use cases for industry, governmental agency, and academia. And we wrote on the proposal that we also want to act as a hub for these mandatory engagement. This is very difficult at the moment, and we have to see. And of course, all of this is closely connected to the Center for Quantum Technology and Applications. And in the moment of statistics last Saturday, I went to HED Inspire and I tried to find qubits. And you see the figure on the right, since 1996, basically there was no paper about qubits. In the last year, this has really exploded completely. And since 2020, there were almost 2,000 papers with the title qubits. It's not only qubits, it's also that people have started to use qubits. So qubit is something where we not only have two states, 0 and 1, but more states, like 5 or 7. And we can really address all these states, for example, through lasers. And this gives you much more flexibility and much more space to do quantum computation. This is rather recent, but I found already 124 papers that have qubits in the title. And last but not least, I also looked for findings similar to simulating physics with computers. And again, on the right, you see that this data came out of relevant citations and discussions about this paper. But then, rather recently, there's this explosion of citations of the paper. There is more than 3,000 citations. And I think this all shows that quantum computing is not really internal or not, that people are really looking into this as many different applications and really performing also calculations on the quantum computers. And why is this so related? I really put the focus on applications in metaphysics and complex metaphysics. If you look at the phase diagram on what we believe is happening in the world universe, then if I do Monte Carlo simulations and I look at the temperature dependence, then I basically can only do simulations in one domain here. If I add a certain metal density, Monte Carlo simulations fail, and therefore the most part of this phase diagram is really completely unexplored. And we don't know what's happening theoretically in neutron stars, whether all these new phases that are predicted when the metal density is very large. So, if you be able to also simulate zero metal density, this will shed a complete new light on the phase diagram and the behavior of the universe. And this is something that interests me personally a lot. There's also the topological terms. If you could add topological terms to the conversion that is used in Monte Carlo, you could shed light on CP violation, you could shed light on the question why there is no metal and antimatter in the universe, so why do we exist? If I look into condensed metaphysics, I could investigate topological materials on a microscopic level and really have a feeling about it. Most of these things lead to a sign problem that really prevents Monte Carlo to look at these problems. In the meantime, the dynamics is the same. It is basically impossible to use Monte Carlo in the Euclidean time to look at real-time dynamics. So we need to have some theoretical understanding about, for example, ion conditions or scattering processes, or we want to study trenches. This is essentially not accessible to Monte Carlo method. And this extends to very hospital observables like partial distribution functions, PDS matrix, and you see there are many other things that is really blocked with Monte Carlo method. And the solution for this would be, of course, the Hamiltonian formulation. The formula directly is the Hamiltonian, and in this formulation, all these problems would not appear. Now, the Hamiltonian formulation has a problem itself. We have to determine the wave function. This wave function has certain basis states, I1 to In, and it has a coefficient matrix. And the coefficient matrix has a size that grows with the number of basis states is 2 which means that the probability scales exponentially. And if you really at the scale with the rise column, the median value, this is the median tower, the median tower, this is the castle here, and the median value would be covered with rise very, very soon. There are two solutions to this. The first solution is tensor networks, where we really reduce the size of the Hilbert space dramatically. Really dramatically. If you consider that local Hamiltonians, then you can prove that you have an area, which means that you have a very fast, sometimes even exponential convergence in the size of the tensor networks. And this is all done in the Hamiltonian formulation. The drawback is that it is very costly, and if you look at problems where you have entanglement, you have a high degree of entropy, which happens, for example, if you look at phase transitions, or if you have real-time evolutions that are very long, then the entropy scales linearly, which means that the size of the tensors that you have to employ scales exponentially. The other solution is quantum computing. This is a conceptually very key part. There is no obstacle, but at the moment, quantum computers, as you also heard before, are very noisy. We have not a much number of qubits, so this is really something that still has to be developed, and as people before already showed you the size of the transistor, which was also quite something, and we are not very far from this, and there needs to be a lot of development. Now, in this talk here, I will really focus on the quantum theories and came out potential networks. And this is a quantum computer from the outside. It looks very nice. You can put it in the living room and stare at it, but then you cannot do much with it because the development, as I was shown in this ideal roadmap, is so fast that such a quantum computer will be outdated very, very fast. Now, there are many qubit pairs. There are superconducting qubits which are fast, they have high fidelity, but they need cooling and tuning, I will show. There's trapped ions, this is very high fidelity. They don't need extreme cooling, but they are slow. Then there's photonics, there's nuclear atoms, there is silicon spin, quantum dots, analog computing, adiabatic computing, so many things, and it is really still unclear which of these approaches into quantum computers will be in the end. Let me give the example of superconducting qubits, and let me show you the quantum computer from the inside. The chip is somewhere down here, and then this is shielded to 50,000 times less than Earth's magnetic field. It is in a very high vacuum, the pressure is 10 million times lower than atmospheric pressure, and it is cooled almost 200 times colder than interstellar space. So we are working at 0.015 Kelvin, which is really a tremendous engineering challenge. And this is, of course, all around to prevent any quantum noise, to prevent any interaction with the environment. Because if you have any interaction with the environment, the quantum nature of your state will be destroyed. You will know that the cat is alive or dead. And you want to keep the quantum state. And for this you need all these measures that are listed here. You look at really IBM has a very aggressive roadmap. We have machines with 156 qubits this year. And what we are promising is that there was also an error. In 2029, we will have error correction and we will have parallelized chips. On the chip down here, you may place something like 400 qubits, but not more. So in order to extend the system, you really have to go parallel. And IBM is working on this and realizing this in various ways. And this date, 2029, for error correction, is not only IBM, also Google promises that in 2030 we will have 1 million qubits, out of which 1,000 qubits will be error corrected, and I believe that with new algorithms that we have, actually the number of error corrected qubits will be larger. And it's also, again, it's not only Google, it's also Continuum and other companies. They promise that by 2030 we will have quantum computers that are error corrected. And this will be a complete game changer, because then we can use the quantum computing as you use today in your laptop. So I propose that we really look into how you can how you can program the quantum computer such that you are ready for that era. And okay. And you can really do this. The companies provide really libraries, everything. It's an programming environment. It's not magic to program a quantum computer. Let me stop here and ask whether for this part you have any questions so far. I need to ask Fernanda to look into the chat and tell me.
So there is one time, if there is one, you just let us know.
Yes, please. Please. Okay, and let's really have a look what we can do with a quantum computer. And for me, what I wanted to do here today is to really show applications in quantum molecular mechanics in 1 + 1, 2 + 1, 3 + 1 dimensions. So let's start with 1 + 1 dimensions, and let's have a look at the Schwinger model in the continuum. So the freedom model has further independence of freedom, denoted by psi here. It has the H covariant derivative. This A is the gauge potential. It has a mass term, and it has the electric field operator, so the time derivative of the gauge potential, and you can also add an external electric field theta. And such a model has already a very interesting phase diagram. So if you plot the phase diagram, it's a function of m, the mass, divided by g, the coupling of the gauge potential to the metal fields here. Then if you go to the very large values of m over g, much larger than 0.33, you have the first order phase transition, which is actually CP violating. This first order phase transition ends in the second order critical point around m over g equals 0.33, and this happens at the value of theta over 2 pi, which is 1/2. This means that this value of theta is so large that you cannot do the Ricardo simulations to explore this phase diagram or to explore the region when there's no phase diagram. I thought there was something in the chat from us.
Carlos, just saying that there was no question so far.
Okay, good. And this means that maybe to explore such a phase diagram, it's basically impossible to explore this Monte Carlo methods. So the question is, can we have a total formulation in quantum computing, can we explore such a phase diagram? So the first thing we have to do is we have to discretize this. So we have again some matter fields, the field is phi, and to couple these matter fields with lattice points n, and lattice point n plus 1, and then you have a gauge field operator un that points from n to n plus 1, and this is related to the gauge potential in this form here. So this we call it a link operator, is e to the I, the lattice spacing A, the coupling G, and then the gauge field operator. And this was actually really the major observation of Wilson, that you should work with this link operator and not with the gauge potential itself. So then you have this kinetic term here, with the Hermitian conjugate. You have the mass term. If you use what we call Wilson terms, you have a divergence 1 over the lattice spacing. So if the lattice spacing goes to 0, with the divergence you have to take care of this. You have to take care of this more alternatively. I will not explain how to do this exactly. Then you have the electric field operator and then the external electric field. So this L0 is simply theta over 2 pi. And we have to determine what we call the mass shift. It's not so important here, which allows us to get rid of this divergent term towards the continuum limit when we set the lattice spacing to 0. Now comes the point, and this is really important because this is a general way how to put such a model on the quantum computer. And this goes through a general linear transformation. So we do a relabeling of the original field to the sky field, and then this sky field can be expressed in terms of power matrices. So we have the third power matrix, sigma 3, and then we have either sigma minus or sigma plus, so sigma 1 plus I sigma 2 divided by 2 or minus, and then you can rewrite the Hamiltonian flow in the dimension this way by introducing this value x, which is 1 over the lattice spacing squared. And then you get to the form of the Hamiltonian, and I will not go into the details, but the only thing that is really important here is that you can express this Hamiltonian solely in terms of power matrices. And power matrices can work directly on the QH, on the two-state system. So and then you have immediately transformed the continuum Hamiltonian on the lattice in the form that you can use it directly for the quantum computer. So we have done this. And in order, what we want then is we want really to find the lowest energy of this Hamiltonian, and this is done at the moment very often with something that is called variation quantum solver. So this is a hybrid quantum classical variation approach, where you start with the qubit Hamiltonian, exactly the Hamiltonian that I showed you before, which was expressed in terms of Pauli matrices. Then you have a choice of an ansatz. An ansatz is simply a particular form of a quantum circuit, and I will show you quantum circuits in the next slide. And then you start, and this parameterized quantum circuit has parameters, theta parameters. Don't mix this up with this external electric field, let us realize. You have a certain initial state of the qubits, let's say you put it all to zero, and then you run this parameterized quantum circuit. You measure the state that you get, and then you determine the energy of the system that you get from this parameterized quantum circuit that you have initialized, for example, randomly. Then you give the parameters and the energy to a classical optimizer. Think of conjugate gradient or your favorite classical optimizer. And this optimizer will tell you, I believe your energy is not your energy. I run an algorithm to give you a better set of parameters that brings you closer to the energy of the Hamiltonian. You put this in this parameterized quantum circuit, the same initial state. You measure again, you give it to the optimizer, it tells you you are not yet there, and that's overweight. And at some point, you get at least close to the minimal energy of the Hamiltonian. And this is what you want, because then you have the ground state energy and also corresponding ground state wave function. And with this then, okay. And these are typical quantum circuits. So this is what we call SO4 or Rx plus YY. And they can be made with rotation gates. So these are Z gates. So these are rotations around the Z axis. You have entanglement gates, these are CMOT gates, and then you have more general rotation gates, and again the CMOT gates to have entanglement and rotation gate. So you can really transpose this SO4 or this RXY gate into basic operations, into basic game operations that you can use in the quantum computer. And then you can use an ansatz, so a certain pattern where you use this parameterized quantum circuits. And for example, you can use the break ansatz, so you really entangle in this way here that you have this lever, so you can have a ladder ansatz, so you can really go on this diagonal here. And one important point is that nobody tells you what is the best ansatz you should choose here. You can put in certain symmetries, for example, charge conservation, and it's really an art, and you have to try out a lot of things to see which form of such an ansatz you should use. And for us, it was in the end this SO4 and Rx plus YY that we have chosen, either on the break ansatz or the ladder ansatz, but this might by far not be optimal. Nevertheless, we did quantum simulation on the idea in quantum hardware, and we looked at this phase diagram, and our first point was to go to very small values of n over g, 0.1, so we are down here in the phase diagram, and we value this at 0, which is theta over 2i, and indeed, looked at this very small value of n over g, so a completely smooth behavior. And what is really nice here is the thing that you don't see. And what you don't see is a difference between simulation where we use the exact diagonalization of the Hamiltonian and where we use the exact simulation, so it's a sort of state vector simulation where we don't look at quantum nodes in the simulation and the crosses which actually are the ones in the IBM quantum hardware. And you see that these runs in the quantum hardware match almost perfectly the exact simulation that we did, which is very promising. And the same is true when we went to very large masses. So we said n over g equal to 10. So we are somewhere here in the phase diagram. measure the expectation value of the electric field density, which will be known by L, and the particle number. And again, we vary this L0 parameter, which is theta over 2 pi. And we clearly saw that we have a jump behavior, so indications of first order phase transition both for the electric field density and also the particle number. And this we could see for the system size of 3 lattice points, meaning 6 qubits, up to n equal 6 lattice points, meaning 12 qubits. And again, what you see here includes exact randomization, exact simulation, and hard variance. And you see that with the algorithm part here, and with the help of algorithm people, we could not only detect such a first order phase transition, but we could really match the exact results. I think before I go to focus on the dimensions, of course, also here and ask whether somebody has a question to that. So when this last time, not so far. Okay. Thank you. Then I really strongly understand it. And we understand it really that we now assimilate to generic quantum field theory. So this is now quantum molecular dynamics in 2+1 dimensions. You recover or you see again this kinetic term with the matter field psi and the mean operator u. And this is for the experts, this is theta fermion, so you have a phase, you have the mass term, and you have something new, meaning you have a magnetic term. You remember that we showed before, it was only the electric field operator that played a role. In 2+1 dimension, you have something that is called a packet operator, which is the product of these units that are here around the packet. And this then really leads to interesting effects because you will have an interplay between the electric field and the magnetic field. And this is really then becoming very interesting and it's really effects of generic quantum field theories. And what we did here is a work together with Continuum, Hartley manufacturer, and we look at the static potential in 2+1 dimensions. Static potentials means that you have two charges, two opposite charges, and these charges have an infinitely heavy mass. And you can compute the static potential, at least the generic form of it, and it has a Coulomb part, which in 2+1 dimension is the logarithm of the distance between the charges, and you have a linear part that is needed to confinement. So you have this part here, you have a Coulomb part, the logarithm, you have a linear part, and then at some point, the string that holds these two charges together and leads to a linear potential will break, meaning that for the system it is energetically more favorable to create two mesons out of the vacuum instead of really stretching the string even longer. And this is really a typical behavior that is also in QCD, and it's actually a phenomenon that the standard Monte Carlo simulations it's pretty hard to observe. Okay, and in this potential we have the coupling, which depends on the distance between the charges, so it is a random coupling. We have the string tension, which is meaning the strength of the string. We work actually in fixed distance in lattice units. So we have, let's say, a 3x3 system, and we use a distance that always spreads over 3 lattice points. And what we do is then that we use the fact that the lattice spacing itself, the physical value of the lattice spacing, depends on the number of the gauge coupling that you have in the system. Which means when you change the gauge coupling in the system, you also change the lattice spacing, and therefore, if you have the fixed distance in lattice units 3, you change the physical distance. And this is plotted here, so this is the potential, and the fixed lattice distance as a function of g, meaning that this is a function of the physical distance. And what we want to do, we want to see do we get this static potential from the quantum computer? And actually, can you also look at the electric flux configurations to really get more insight into the small regions of the static potential? And you see, if you look at such problems, the quantum circuit already becomes immense. You really have to work on it, so we use something that is called mutual information. It's a measure of entropy between the different lattice. You also use mid-circle measurements. This means that when we have a line where the qubit becomes idle because it has already been used in the calculation, you can use this qubit to do another task, and therefore you can reduce the number of qubits that you need theoretically to substantially less. So in this case, when we look at the four-battery system, we needed actually 24 qubits, but through this mid-circuit measurements, we could reduce it to 16, and this allowed us in the end to really make a hardware run on the Continuum H11 system. And this is plotted here. So we use the Continuum H11 system to perform inference runs. This means that we optimize the parameters in the variation quantum mining solver classically, and then we use these parameters in one run in the hardware to see whether we get an equal state that we also got from an exact simulation. And to see whether the lines are from a noiseless simulation, and these are hardware results with different shots, 1024 shots or 512 shots, so repeated measurements on the quantum computer. And again, you can see that the accuracy by which we could map out the static potential is actually very good. So we can do 2+1 systems on the quantum computer and split this. And for me, this is really interesting because in 2+1 dimensions, you have something that is called Schoen-Simons terms. And these Schoen-Simons terms, they are really relevant for topological materials. And to see what you can do when you derive this Hamiltonian, again, I don't go into the details, but what you will see is that if you don't have a Schoen-Simons term, and you have a pure maximum theory, then this becomes gapless, the photon is really massless. If you add a Schoen-Simons term, you have a topological mass generation of the photon. So this is really a topological effect that you can only see when you add a topological term like this Schoen-Simons term. And this really opens a completely new door, because this means that you have a microscopic description of topological materials. So you can look at, let's say, fermion boson modalities, fraction quantum Hall effect, or really develop new topological materials. And for me, this is really a very nice development in 2+1 dimensions, and we are presently working to bring this really to numerical simulations and see what we are getting. Finally, I simply want to say that we have also developed the Hamiltonian as a topological term in 3+1 dimensions. And with this, we could calculate, let's say, the topological charge. And if you know beta, this beta here, which is 1 over the gauge coupling square, and you make it small enough, then you see the charge transition in the region of the first order phase transition as a function of the topological parameter theta. And this is again very promising. We are trying to do this on the quantum computer, which means that we are now living in a phase where we go away from time models like in 1+1 dimensions, but really looking at physically relevant models in 2+1 dimensions and 3+1 dimensions, with additions to the Hamiltonian that leads from the Carter simulation basically to be impossible to investigate. That's kind of the project that we have. I want to mention that quantum computing is really the only thing. We mentioned already in slides that there are tensor networks, and we also working in the Hamiltonian formulation. And there's in particular the scheme as the movement of Gero, we have swapped with tensor networks and 2+1 range of QD of finite density. up to 16 by 16 lattices, and they will really explore the phase diagram and the density profile and detect different phases with different orders of the charges. They are even already also in 3 dimension, and you see again the starting potential, and they are able to map this out in 3 dimensions with tensor networks. So tensor networks in the quantum community will basically in parallel. There is still an open question about what problem we should use maybe tensor networks, and for what problem we should use quantum computing. But people are really in contact with each other and try to see what is the best method for what problem. So are there questions up to this point? There's 2 things again. Question? Yeah. I skipped the middle gate series, it's going too far. I'll go to real-time moments. This is really something that seems to be the application for quantum computing that is most promising as an application. Because as I said before, we really are interested in long-term dynamics in the entropy scales linearly, and therefore tensor networks will become extremely costly. So what do we do with quantum computing? The scheme is always the same. This is the scheme we have to create the vacuum state, and the ground state of the heterogeneity of the system that we want to investigate. Then we have to generate a wave packet in a certain way, and then we do a time evolution. If you want to time evolve a certain times t, then we do totalization, meaning that we cut this into time steps, the total time t times the number of time steps you want to do. So this has the elements that you need to compute the ground state of the considered middle. Then you have to generate a hadron or whatever wave packet on the ground state. Then you have to do a real-time evolution of the wave packet, and then you measure relevant observables. The algorithms that we are using is again variation quantum eigensolver to prepare the ground state, the totalization for the time evolution, and something that is called Units rotation is important here, both for the wave packet generation and partly also for the time evolution. And then we have to think hard about the ansatz and quantum circuits that we want to use. We want to use a bit better really employ symmetries, and this is really hard work before we can start something. There was a randomized paper by the School of Martin Sedgwick, and we extended the basic variation of quantum eigensolver that I explained to you and scalable circuits adapting to you, which means adapt is that you have really a set of operators that you use to really project better in the ground state, and you can make these operators according to the fidelity that you get. And the basic idea here is that you bring your quantum algorithms on a small system. Let's say in the Schneemann you have, I don't know, 6 sites. You crank up this machinery, you find the best parameters in this variation quantum eigensolver, then you repeat this on the system with indicator response, again you find the best set of all the parameters, and at some point, when you run out of steam, you try to extract these parameter values to large lattices, and large lattices means here that these people have used already 100 qubits. So really far beyond what I showed you before in the Schneemann. Again, you have to work on the quantum circuits. I don't go to the details here, but you see there's always the same rotation gates, you have entanglement gates, and it's really, you have to think hard what you use for the problem under consideration. Yeah, and then this is the real hardware is covered, so here is the wave function on the ground state. You have more than 100 qubits, and then your time evolving this wave function leading to pretty large time. And this was what I'm showing you. This is actually a plot from the quantum circuit. Sorry, from the quantum hardware. We ourselves have done something similar, but in the same level. So we generated a Gaussian wave packet, given here with a certain mean and a certain width. This you can do also with Newton's rotation. And then we looked at the time evolution of this wave packet for first of 3 minutes. And what you see is you generate, because we wanted to look at the scattering of the wave packets. And what you see here, there are 2 wave packets, so you see the answer is there. And then the timing of this wave packets, and since these are 3 terminals, they don't see each other, they just go through each other. These are very boundary conditions, so when this wave packet ends up here, it reappears here, and so on and so on. So this was just a proof of concept that we can generate this wave packet and that we can time evolve it. Again, I wanted to show you that the quantum circuits for doing all this, they become really massive. We had all these symbols, R1, 0, and so on. There's really something that has to follow, that you have to compose the terms of rotation, gains, and determinant gains. And the development of such a circuit and to optimize such a circuit is really at the heart of the quantum computation that we're going to do. And here you see the result. This is again the scattering of the wave packets. This is the coupling 0. So the wave packet just go through each other. This is the coupling of point 8. And what you see is that you have a repulsive force. So the wave packet comes here and hits the red wave packet, and then you see a repulsive force in the scattering of the wave packet. So this is a real physical phenomenon. In a model where you would expect that you have such a repulsive force, and this is very nice to see. It also measures the entropy, and what you see is that after the collision, you have some entropy. This is this yellow color, the yellowish color here, and even if you subtract the entropy of the single wave packets, you can see that if you have a zero coupling, there's nothing left, because there is no scattering, so the particles don't see each other. But if you have a coupling of 0.8, then you see that there is a remnant entropy. You can really see that these particles, after the collision, they are entangled, they know each other. And I think this is a very nice and interesting direction to look at also for the eventual analysis of data at the LHC. And then we went on and we said, okay, let's do such an experiment. So this time evolution of the wave packets. And then we said, can we really do this on the quantum hardware? And we didn't do the full time evolution, but we took snapshots like a time equals 0 and so on. And here is the plot where we have looked at the subtracted entropy, so the last row in the last slide. And what you saw, and I always forget which of these points is an exact simulation in which when you see is the other one, it must be the one you see error on, and you see that really from the hardware we get very, very close results from the exact simulation. And here we went to like 12 qubits. My colleagues now working like 64 qubits and really have meson scattering and things like this. So it's really developing, and I just show this here. I flashed this here with all these people are working to improve this time evolution in quantum computation. It's a very active field that we are following. Maybe that's a skip because of time. Sorry for that. But Fernanda is living in quantum computations for quantum distribution functions, so yeah. But I wanted to show you that we are really that people are really coming together in our field of energy physics. There's a quantum computing for energy physics white paper that was led by Soren Bertolini, myself from Daisy, and Ivan Tavanelli from IBM. What we really wanted to do was we wanted to come together and identify applications that can run already now on the quantum computer. And we did this both for theory and also for experiment. So we really identified the algorithms that are available, like I told you, this variation quantum Bayes solver, the proper dynamics, tensor networks, quantum tensor networks, the methods that we have, and then also the concrete applications like real-time phenomena, low-dimensional speed theory, quantum ring models, and also material installations. And we really said there is really prospect that we can run this on today's quantum computers. We did the same for experiments, again, the algorithms, the methods, and then new applications like jets or threat reconstruction, rare signal extraction, or looking at beyond the standard model processes, part controllers, and even simulation experiments. This was to a large extent a European effort. Colleagues in the United States, they put out similar paper, coding simulations for energy physics, which you can find here. Now this is really showing that we are not working in complete isolation, but that we really come together regularly and try to identify what can be done with the quantum computer. Okay, so today I would say that we are really able to simulate the building and modeling POV series in two spatial dimensions. I showed you the example also for QED, quantum molecular dynamics in 2+1 dimension, where we also couple metafields. People are also looking at the base models. I showed you the example of looking at topological terms, which is relevant for CP validation in 1+1 dimension, and Artin distribution functions for simple models. Let's think about transitioning now to an era where we also look at normal gauge theory and the gauge theories in even 3 dimensions. This means that I think for a start, we can look at quantum molecular dynamics in 3+1 dimension. This will happen this year or latest next year. And this will also allow us to look at modeling equations and in topological terms, both looking at metaphysics, where it is relevant for topological materials, but also maybe in 3+1 dimension, where it is really interesting to look at topological terms and the amount of CPU evaluation. And then tomorrow, we can really looking at SU3 in 3+1 dimensions, which would lead us to kind of proper dynamics, and we could then simulate this with a topological term. I would find it really interesting to also look at Chi-gate series, which we don't understand intuitively, where we don't have a chance to do something with Monte Carlo methods. We can also, of course, look at extension of the standard model and get non-zero meter density. Yeah, and then I could ask you to, we are doing real-time simulations that show you terminalization, scattering, quenching. This can be extended over the next years to really look at collisions at the quantum plasma nuclear physics. Conformal field theory, you can actually theory application where there are the dots, and this can give us completely new insight in Nobel's matter and energy physics. That was this, and thank you for your attention. And maybe now you have questions. Yes, that with the formulation, and with action formulation, you need a positive probability density. In the Monte simulation, with a Markov chain, then you have to ask the question whether something is larger or less than something else. Or if you do the Monte you simply sample randomly. Now, if you add terms that relevant, for example, in non-zero density, then this action becomes complex. And if this becomes complex, you will not have the notion of probability density anymore. It doesn't make sense to ask whether something is bigger than the other. If you go pure Monte Carlo and random sampling, then you have to randomly sample a phase, and for this you will need the age of the universe to get any reasonable result.
Price case here.
So first question was the lattice volume?
Yes.
Yeah, about the lattice volume. Okay, so we are going in 2 plus 1 dimensions to further 3 lattices at the moment. I think we can do more with the next generation of quantum computers. I showed you the example that we have in 1 plus 1 dimensions already more than 100 lattices. So this is the typical thing we are working with at the moment. Okay. The second thing, in theory, we are looking at, they are fully non-attributively engaged invariantly defined. You don't have to fix the beat. You will always completely engage in etc. What you need to do in the Hamiltonian formulation is that we respect Gauss law. So we have to respect that the incoming electric flux equals to the charge that it hits and the outgoing electric flux. But these are the 2 conditions that we fulfill, that we have a fully engaged invariant system and that we have to respect the Gauss law. But we do not have to fix the gauge. And these are the QED or the QCD. This is just when you want to do perturbation theory. And this was the big step of Wilson, that he said we can do it in a fully engaged invariant manner without needing to fix the gauge. And this is what people in lattice QCD are doing since 40 years now. Okay. Okay, thanks a lot. Thank you so much.
É, o problema nosso é que fica em dois microfones. Né?